Now we introduce one of the main algorithm design ideas in this lecture, divide and conquer. So the idea has three parts. So first, we divide the problem into smaller subproblems of the same general type. Second, we conquer the subproblems, and what we mean by that is that usually what this means is that we solve them recursively. And third, we combine the solutions of the smaller subproblems to get a solution to the original problem. So the basic pattern is divide, solve recursively, and then combine. And so this will often lead to recurrence relations, and typically of this form over here. And so let's understand what this is saying. So here we can think of T of n as the running time for some problem of size n that we are analyzing. And the idea is that this problem T of n, we're going to break it into solving smaller problems of size n over b, some factor b. So the idea here is that T of n is going to be, this a here represents the amount of subproblems. This b is the factor by which the subproblem shrinks. And this f of n is sort of the cost of dividing, combining, and other stuff related to the problem. So some function here of n. And so, for example, let me do a little box here. So for example, for binary search, what we did was we essentially broke the big problem. So the big problem of binary search, we broke it into one problem of half the size. And then there was this one cost that you had to do for checking the middle value. So that was like the extra guy outside. So in other words, our A here is equal to 1 for binary search because the amount of subproblems that we use is just 1. The factor of how smaller it is 2. And here the extra costs, in this case, it's just a constant 1, right? And so this is, now we want a general way of dealing with things like this. And that's where we're going to use something called the master theorem, right? So the master theorem is a very strong theorem, powerful theorem for solving recurrences that take this form over here. So again, you can think of this as the cost of whatever you're analyzing, and if you're able to break it into some constant amount of smaller versions of it, plus other stuff that goes like n to the power of some d, then the master theorem is going to tell you what is the asymptotics of this f of n, right? So let's interpret this carefully. So the number a, again, is the number of subproblems. And then the idea is that the b to the power of d here, so this b to the power of d here, so b again is how much you divide the problem, and this d is sort of getting what is the complexity of the other stuff you need to do. So this b to the power of d measures how much the non-recursive work shrinks when the input size shrinks with n to n to the over b. And so there are three cases. When a is smaller than b to the power of d, then essentially this part is gonna dominate and you get something of order n to the power of d. In the case where these two are equal, this a and the b to the power of d, what will happen is that you're gonna get sort of like a balanced work, and so you're gonna get the n to the d cost, but with an extra log n. And then if a is larger than b to the d, right, then in that case, essentially what you're going to get is that what will dominate the cost is going to be this n to the power log a in the base b. And so if we look again at the binary search example, so we had seen, so the binary search was you transform the problem into half of its size, and this was for checking the middle value. So it had a equal to 1, b equal to 2 here, and for the binary search, the c is equal to 1, right? And the d, so it's an n to the power of 0 to get this 1 over here, so the d is equal to 0. So if you replace all of these, you get case 2, because you'll get that a1 is going to be equal to p to the power of d, which will be 1. And so it'll give you the second case. And in this case here, d is equal to 0, so this will just be a 1. So you get just this order of log n, which is what we got when we analyzed binary search.